All right, so today we're going to look at angular momentum. Now, angular momentum is very similar to just regular linear momentum, except, again, you're looking at angular components. So it follows the same kind of formula that we use for momentum, where it is mass times velocity. And it is still the same thing. It's talking about the quality of motion, but this time we're looking at rotational motion. And so what we're going to do is we're going to convert our P equals mv, because momentum is the MVP, back to angular terms. And so what actually happens is, just like before, m turns into I, and velocity turns into omega. So we have the angular velocity, or angular momentum, is equal to the rotational inertia times the angular velocity. So the symbol for this actually looks kind of crazy. It's an L, a capital L. It is not a Greek letter. It is just straight up L. And the real reason behind this is not really known, other than you're just kind of following the alphabet and they landed on L. I'm like, great, that'll work. We haven't used that in a while. So the symbol is a capital L. Now, if you look at the units, we know for the moment of inertia, it is kilogram meter squared. Because remember that I is equal to the sum of mass times the radius squared. So that's where the kilogram meter squared comes from. And we know that omega is in radians per second. So if we're looking at the units for L, it's going to be a kilogram meter squared per second. So nothing fancy there. Kilogram meter squared per second. And again, the equation that we need to know is that the angular momentum is equal to the rotational inertia times the angular velocity. Now, direction is going to matter just like before. This is considered a vector. It's going to have a direction. We'll talk more about that in a second. The next thing that we have is rotational impulse. Now, just like before, we had the equation that impulse was the change in momentum, which was equal to mass times the change in velocity. But another way of writing that was to say that it was equal to the force times the time. This is the one that we're going to look at. Because if I'm talking about the change in angular momentum, we're going to use the linear or the angular component of force, which is torque, times the time. So for rotational impulse, the symbol is typically just written as delta L. Rotational impulse. And the equation is torque times time. And when we're looking at the total, it would be the net torque that we're looking at here. Now, this is useful because if you have a torque versus time graph, this is what you can expect to see, torque versus time. If you have a varying torque, so let's say it goes up like this, then if you want to find the change in angular momentum, all you need to do is find the area into the curve. Because if you think back to your other equations, this is like length times width, and when you are multiplying both of the axes together, the area is going to give you this. You can also see it as torque is equal to delta L over delta T. So if you have the change in angular momentum over time, that's going to be the slope, and that slope is going to get you the torque. So always nice to be able to manipulate those equations to read a graph. All right, so talking a little bit more about what this actually is telling us, there's kind of two different ways you can look at rotational impulse and rotational momentum. The interesting part is that every object has angular momentum, every single one, even if it is traveling in a straight line. Now, the reason this is the case is because this object, if it was traveling in a circle around P, would be traveling like this. and we are looking at its tangential velocity. Now, when it moves to a different place, if it's cutting across the circle like this, then as it moves closer and closer and closer, it's joining a new circle with a new tangential velocity. So as it gets closer and closer and closer, the radius is going to decrease and the actual velocity is going to increase. Because again, more of that circle, if you're looking at the components that are in this direction, more of that circle is going perpendicular as it gets closer and closer and closer. Then that's going to decrease as it gets further and further away. So another way of writing this, when we're looking at our linear or angular momentum, is to say that it is the mass times the velocity times the radius times the sine of theta. Here's our secondary equation here. Now, because we're looking at the sine of theta, that means that really what we're looking at is the r perpendicular. So a lot of people will write this as mvr perpendicular. Now, here's why this actually works. Because if you have L equals I omega, and you want to convert this into values that are pretty easily measurable, we have I, which is mr squared, and omega, which is velocity divided by the radius. Now again, that is tangential velocity there. Well, one of the radius is going to cancel out, and we just have mvr. Looks like this. Now you could write this as the momentum times the radius, which means that L is equal to P times R, which is just like all of our other terms, where you're taking that component times the radius to get your angular component here. Just like how we had torque was equal to force times radius. See how they are exactly the same? Which is pretty helpful. So this is going to be our linear momentum. And this right here is the radius of the circle. All right. Now, when we're looking at this part, we're going to be finding the angular momentum at different situations. So we're going to apply what we just looked at. So in the first one, we have car X, which car X is over here. That is the setup right here. It has a mass of 1,000 kilograms. We know that it has a speed of 10 meters per second. That's going to be the tangential speed, or the linear speed, if you think of it like that. So we now know that v is equal to 10 and travels around a circular path with a radius of 100. So r equals 100. I'm going to write that on my picture too. So we know radius is 100, velocity is equal to 10. There's a flag in the center of the track, and points A and B are on opposite sides of the track as shown. We're going to look at car Y in a second. Let's focus on car X, and let's figure out all our information. So we have car X when it is at point A. So in this case, quite simple. We can just say that the angular momentum is mv r perpendicular. So we have the mass, which is 1,000 kilograms. We have the velocity, which we know is 10 meters per second. And then we have the radius, which is 100 meters. Now the reason I can say that it's 100 is because since this is a circle, the radius to point A is still 100 meters. Great, so I'm just going to multiply all this together. And you have 1 with 6 zeros meters. Oops. And then we have the units, which are in kilogram meters squared per second. And that is my answer. Now, when I go to point B, I'm asking myself what's changing. Well, it's the same exact car, has the same mass. It's traveling at the same speed, and it's the same distance away. So nothing changes. All right, now we're going to switch over to car Y. So car Y travels on a straight road with a speed of 10 meters per second. We know that there is a flag that is 100 meters from the straight road, and point C is closest to the flag. So what that's just telling me is that this distance right here is perpendicular. That is the shortest path. There is a flag that is 100 meters from the straight road, and point C is on the road that is on the point closest to the flag. Point D is 200 meters down the road from point C. So this distance right here is 200. We want to find the angular momentum at each of these locations. Okay, so same kind of thing here. We know that this was 1,000 kilograms, just like before. Now, when we're looking at point C, it's easy because they tell us what the radius is. So we know that L is equal to mv r perpendicular. So we have 1,000 times the speed, which is 10, times the radius, which is 100. So we get the same answer. Don't forget those units. Now, unless there is a torque that is going to change it, we have this conservation of momentum. We have the same momentum before and after. So what we should see at point D is exactly the same momentum. Try this now. All right, looking at point D, we still have mvr perpendicular. Now again, you can look at the velocity perpendicular or you can look at the radius perpendicular, but it's way easier to look at the radius because we know that the mass is 1,000. We know that the velocity is 10, and we know that no matter where you are, the perpendicular radius from wherever you are, even if you're all the way over here, the perpendicular radius is 100. Still 100 meters. Doesn't change. And so, when you multiply all this stuff together, you get exactly the same answer as before.